Well, welcome back to the Physics Lounge. We're taking a look at the Level 2 NCEA Physics paper for 2022, all the papers, starting with waves. So I hope you read all that stuff on the front, it's important, particularly SI units, which I think are severely underrated. That's a physics teacher, hobby horse. Question 1, behaviour of light. Helen is investigating wave behaviour in the school physics laboratory. This is a very unimaginative context, sorry, but you know, in your school lab, okay. It's probably where most of you are going to investigate light though. She starts by shining a ray of light from air into a glass block, so that the angle of light inside the glass is 32 degrees as shown in the diagram, okay. So a little bit of guesswork here because of the missing diagram, which you can look up if you follow that link from Wikipedia. I don't know why they don't draw their own pictures. So it's 32 degrees inside the diagram. So if we make our glass block here, we've got some sort of angle of incidence. I haven't seen the actual paper, so I'm just giving you my best guess of what the diagram would be like. And it says 32 degrees inside the glass. So this would be 32 degrees, and so would as it exits the glass if it's going out. So those two angles would be the same. Yeah, I don't think it would make sense to have 32 degrees as the other angle. That would probably be too small. Anyway, calculate the angle of incidence. So N1 sine theta 1 equals N2 sine theta 2. So same old here. It's going from air into glass. So I would typically make number 1, so the left hand side, the air, 1.00, so that just means N1 is 1, so 1.00 times the sine of the angle of the incidence that we're looking for here, theta I, equals N2 refractive index of glass 1.52 times the sine of 32 degrees. And you'd rearrange that for sine theta I and do the inverse of sine of theta I, inverse of whatever the other side of the equation is. Okay, you should know that. I'm not going to linger on that. You can watch the videos on the Physics Lounge if you're not sure how to rearrange this equation. The light changes direction as it enters the block. Yes, of course. State what happens to the speed of the light as it enters the glass. Well, it must decrease. Okay, it's a more optically dense medium. That's what the higher refractive index of 1.52 compared to air, 1.00 means. So the speed decreases. Calculate the speed of light within the glass block. So on your formula sheet you have the velocity in one medium over velocity in the second medium is equal to the refractive, let me see if I can get this right, yeah, the refractive index in one medium over the refractive index in another. So it's the reverse. The higher the refractive index here, the lower the speed will be. So they kind of correspond, but in the inverse way. There's also a inclusion of the wavelength. So wavelength 1 over wavelength 2. I think I got that around the right way off the top of my head, going really quickly late at night because we were hoping to get this out quickly. So you would put in your values for, you now know N1 and N2, and you know the speed of light in air. So whichever one you put that in, you would put that in and rearrange. Say if you know V2 is air, then you would rearrange for V1 and calculate that. So Helen now uses a semicircular block and alters the angle that light hits the straight side and observes the following phenomenon. So this is probably a critical angle calculation because that's fairly straightforward, and this is a classic experiment for that, where you have your incident ray coming in at different angles until and it oh, hang on a minute, wrong way. You have your incident ray coming in, having technical difficulties? No. But you have your incident ray coming in directly at a tangent to the surface, so there's no refraction going into the glass. This would be the glass or the perspex. What have we got? Semicircular block. It doesn't say it's glass or not. But either way, that gives you a angle of incidence in here that you can adjust to make it more or less. And you can adjust it until the refracted light, remember it bends away from the normal going from glass into air, so you can adjust it till it goes along the surface. So identify the physics phenomenon occurring at the straight boundary. So again, without the picture, it's a little bit hard, but it's still refraction. If you go increase your angle of incidence enough, you'll get total internal reflection. So maybe that's what's in the diagram. You'd have to take a look. Maybe you need to go and look up that YouTube video. Maybe I need to. But it's probably total internal reflection that they're talking about here. Describe the two conditions required. Yeah, it's almost certainly. So the angle of incidence must be greater than the critical angle, and you must be moving from a more or higher to a lower or less refractive index, or optically dense medium, or something like that. Okay. D. Helen investigates a concave lens. She places a pin at a distance of 7 centimeters in front of the lens. That means, if that's the focal point, that means the focal point is less than 7 centimeters. Oh, there you go, 3 centimeters. So 3, and from there to there it's 7. And it says complete the following, and finds that she cannot form an image on the screen. Where is the screen? So it's a concave lens, so screen would be on this side. Must pause. Right, sorry, I just had a small pause there to deal with a small child who was awake at 11 o'clock at night and needed some help. So where were we? We've got a pin 7 centimeters in front of the lens. It's a concave, appears to be a biconcave lens, and it can't form an image on the screen. The lens has a focal length of 3 centimeters, so it's 3 centimeters on both of those sides. Complete the following ray diagram and use calculations to describe and explain why she cannot see an image on the screen. Okay, so parallel light ray is going to refract, I should say, because this is a diverging lens, as though it comes from the focal point. And then the easiest one to draw here, although it might be a bit tricky on the screen, is to draw one straight through, really poorly drawn, but straight through, meant to be in the centre, the optical centre there. So at the centre there, you would, you would have one going straight through. So the other rays you could draw, just to give a bit of continuity, going through the focal length, and was that the one? It's a diverging lens, so it should be, I don't know what's going on in my brain right now, but clearly these rays are spreading out between here and here, so there's no image going to be formed. If you were going to have an image, you would have to track it back here, and you would have to look at it from this side, and you would see the image forming where the light rays appear to come from there to there. I guess this one would have to spread out that way and track back to that point too, which is a bit strange. I can't remember. There's something weird going on in my brain here, but it's late at night and I just got interrupted, so excuse me if you had some thoughts on that, throw a comment in. Yeah, there's another ray that you could draw. Oh no, that works on different ones. Anyway, moving on. You don't want to hear me ramble. Okay, what was the rest of the question? Use calculations to describe and explain why she cannot see the image on the screen. So your classic calculation would be 1 over F equals 1 over DI plus 1 over DO. So we know DO is 7 centimeters. So I'm just going to go over the top of that in a different colour. 7 centimeters. That's a positive number. The focal length, though, normally we would consider this side to be a positive focal length. So this being the virtual focal point that the rays appear to come from when you're looking at it from that side, would give you a negative value. So negative 3. So when you do this calculation, if I've not confused myself and done this in a silly way, you should end up with a negative value for DI, which tells you that there is a negative image. You can't just throw a negative in front of it. You have to put the negatives and the positives correctly for the F value and the DO value, and then what will come out is DI equaling negative whatever it equals. Should be less than 3 if it's inside that 3 there. Question 2, light waves and barriers. Helen decides to investigate wave movements and barriers. She starts by shining a purple light with a frequency of 7.5 times 10 to the 14 Hz on the wall. I have to change the colour of mine. There we go. Back to blue. Calculate the wavelength of the purple light. V equals F lambda. F being the frequency that was just given there. Wavelength you're calculating, and V being the speed of sight. The speed of light. I don't know what the speed of sight is. That depends on the person looking and whether they register or not. Anyway, a bit silly there. B, she finds an online simulator of wave movement through a gap in a barrier and sets up the 2 simulations below. Complete diagrams to show the effect of the gap on the waves. So on the left hand side, the size of the gap is very similar to the wavelength of the waves, so you'll get maximum diffraction of quite a lot. These should all be the same distance, which should be these distances over here. I'm just rushing through to give you a sense of what the answers were. This one over here, you're going to get less spreading out, and the wavefronts should be fairly flat in the middle and just curving off at the edges, just lightly, just to give it a light curve, whereas these ones will curve heaps compared to the other ones. And again, all the wavelengths should be the same wavelengths as what you have over there, because the closer you get to the wavelengths to the size of the gap, the greater the diffraction. She then shines the same light through a double slit and observes the following pattern. So we've got bright fringes. Looks more blue than purple to me, but there's definitely some purple going on there. Quite challenging if you're colourblind. I don't know if colourblindness affects, probably does a bit, because I know red-green and there's a little bit of red and purple. Anyway, complete a labelled wave diagram to show how this phenomenon occurs. Okay, I'm not going to go through this in a lot of detail, but you've got the overlapping wave fronts, and where crests meet crests, you've got lines of constructive interference where crest meets a trough. You've got lines of destructive interference, nodal lines, antinodal lines, all that stuff. Okay, so they're probably looking for like nodal, antinodal in your labels. I'm not going to get into detail on that. There's tons of diagrams in your books. You should be able to find that one. It's a matter of making sure you give all the detail required. D, use physics principles to describe and explain how the pattern in part C is formed. Start by naming the phenomenon that's taking place. So interference, maybe even 2-point source. Interference, because you've got 2 sources that are both considered to be at a point there. And conditions required for the pattern. So the describe and explain is explaining your constructive and destructive interference. When you're talking about constructive interference, you're talking about crests meeting crests to produce amplitude that is twice the amplitude, and troughs meeting troughs to presumably produce twice the amplitude but in the negative direction, so you're doubling your wave amplitude. Destructive, it's a crest plus a trough, so they cancel out, and that kind of thing. Discussing the conditions required for the pattern to form. Well, you've got a diagram above there, but is there any other information? They may be interested in path difference, although that is something, I know I discuss it at level 2 with students, but it's something I think that is more a level 3 concept, where you look at And I'm pretty sure it comes up in level 2. So a whole number of wavelength path difference will lead to constructive interference, because that'll lead to a crest meeting a crest and a trough meeting a trough. If your path difference is an odd number of half wavelengths between the two waves that are interfering, the two waves, one coming from here, one coming from there, if you end up with an odd number of half wavelengths, that's going to mean a crest hits at the same time as a trough, and then they cancel out. What other conditions? I guess we always talk about the coherence of the two. So this is assumed here, I think, that it's the same wave coming through both. You can't have a nice pattern of interference like this with different wavelengths coming through, but I think I've covered enough on that. That one be interesting to see what the marking schedule says about what they're expecting there. It's a little bit vague. So question 3, light rays and pulses in a rope. This is very contrived, it seems. Like, let's just do a question that has some light rays, and we've got some lenses, and you can see the lens here, and we're going to have pulses in a rope. It's very predictable, and it's kind of good in that sense, but it's boring. Anyway, you don't want to be too exciting in a test, I suppose. Helen continues to investigate light and optics. She chooses to look at the images formed by convex lenses and compares these with mirrors. Okay, lenses, mirrors, don't get them confused. I often do. She starts by placing a lamp in front of the lens and looking at the image formed on a screen. Complete the following ray diagram for the lamp, so the screen's out here somewhere. A lamp placed at 3 centimeters, so that's 3 centimeters from a convex lens, focal length 2 centimeters, so that's 2 centimeters, that's 2 centimeters. So ray diagram, got a different colour. Parallel light ray, converging lens refracts through the focal point, really poorly drawn, but you'll get the gist of it. And then you can have one going through the focal length and refracting parallel. It just happens to be where the screen is there. Again, you're also going to get one going straight through the centre. Oh, that's so badly done. Anyway, if that was running through the centre and it was straight here, use a ruler on your test and try and be very careful with your angles. If you've done a lot of these, you can kind of get away with fudging it because you know where they go, but a ruler is going to make sure they end up in the same place. So here's your image, it's enlarged, it's inverted, and it's a real image because it appears on a screen. B, Helen then tries the same lamp in front of a convex mirror. So this time it's reflecting they're not passing through, nope. They're hitting it and bouncing back in some form or another. Let's just delete those. And for clarity, complete the ray diagram. Parallel ray reflects as though it comes from there because it's a convex mirror converging. A ray that hits the center there will reflect the same distance below as above. You've got your equal triangles and equal angles of reflection, all of that. And it'll appear to come from somewhere there. That's where your image will be, a virtual image, upright and diminished. So it just says complete the ray diagram, and I've just described the image by talking about virtual, diminished, so magnification is less than 1, and upright. To further investigate waves, Helen looks at the effect of sending a pulse down a rope, firstly with a fixed end and then with a free end. Complete the diagrams below to show the reflected pulses from each system. So at the fixed end, where the rope is not free to keep moving, it's going to reflect on the opposite side. You get your phase change. I've drawn that poorly, but it should be same amplitude, and the length of the wave should be the same. So probably closer to that, moving in that direction. With the free end, you can imagine this quite easily. As the ring here slips up the pole, then it has to also start from there on the reflection and slipping down, so it's going to keep the same phase, same side, and again same amplitude and opposite direction. But Helen wanted to see if she could create a virtual image with a concave mirror. This is all over the show, sorry, but what's the link between this here and this here? That would be a nice thing to see, a little bit of continuity for the poor students having to sit this. Getting whiplash. Helen wanted to see if she could create a virtual image with a concave mirror. Use a ray diagram to show how this is possible. So virtual image concave mirror, the key here is to have your object inside the focal length of your concave mirror so that a parallel ray reflecting badly through the focal point there will track back, and optical center above and below, boom, 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 they'll appear to come from somewhere here, and it's an enlarged image. So it's you'll look into that. This is when you're looking into your teaspoon or your shaving mirror, and you appear to see an enlarged image that's upright, and so it's quite good for shaving or makeup, or the dentist tooth, you know, those little mirrors on the stick that are on a bit of a funny angle and they stick them inside your mouth. Anyway, so that's how you would do that. My ray diagram is pretty poorly drawn, but hopefully you've seen enough of those that you can see where I'm going with that. Remember, the key is where the rays appear to come from, and you have to memorize or remember from first principles how those rays will spread out. So describe the position of the object in relation to the mirror. Behind the mirror, I guess. I think that's what that's all about, because it's virtual. It's enlarged, so it should be a further distance away than the object is as well. So if that's X and that's Y, X is going to be larger than Y. That just goes in keeping with the height of the image, because the height of the image should be greater than the height of the object when it's enlarged. So compare the similarities and differences of the image, if any, with a virtual image formed by a convex mirror. Well, convex mirror is your classic security mirror. I'm going to draw your ray diagram really quickly here. Here's our object, virtual focal point, parallel ray that goes in, appears to come from the virtual focal, and then the ray going in that way, that reflects equal angle, so same distance above and below as where the object is. It's going to appear to come from here. That's where your image is. So they're both upright. That's the same thing. They are both virtual. That's the same thing. And the difference is, for a convex mirror, it's going to be diminished compared to the one above. So there we go. That's your 2022 Waves paper. I guess if you're doing this test, you'd be quite happy that there weren't any major surprises in there. Slightly awkward question earlier, but in the first question I think that was. But generally it's pretty straightforward. It's just unimaginative contexts. Maybe that's what's needed when we're dealing with all sorts of other things going on in the world, and people just want some straightforward kind of exam questions. But it's always a bit more interesting if someone's at a playground or looking in a fish tank or a swimming pool, eh? Anyway, if you have some comments or questions about this paper, feel free to put them in the comments below. Like and subscribe and recommend to all your mates and all that kind of stuff, and then have a good old conversation about the physics that you all sat together, and see who did the best. See if I made any mistakes, have a chat, and Merry Christmas, because I'm doing this just before Christmas 2022. So yeah, have a good one. Cheers.